Dear students, we are studying short circuit analysis, and in the last class we have started with direct approach for short circuit analysis. In direct approach, we have seen that we can use direct approach which you have used for load flow calculations, where you already studied those two matrices which are called as BCBV and BIBC, and in this particular approach we can use it for short circuit analysis also. In the last class we have seen that how we can actually divide your BIBC matrix and BCV matrix so that we can use it for short circuit analysis. Similarly, we have seen short circuit analysis for a single line to ground fault, and in this particular lecture we will see few more faults using direct approach based method. So, in particular in the last class we have seen that using your direct approach based method we can write this equation, which is basically delta V, which is equal to your BCBV matrix, which is having structure like this, contains impedances, and then this is BIBC matrix, which depending upon a topology consists of ones and zeros, and these are actually I node matrix. So, these are basically nodal currents. To use these matrices for short circuit analysis, what we did in last class, we have divided these BCBV matrices into different rows. So, we have considered each row of this BCBV matrix and given different names, like suppose you want to consider this row. So, name of this row will be, since it is corresponding to node number 3 and phase A, it will be called as BCBV, and superscript subscript will be 3 because it is node number and phase is A. So, this particular row of this matrix will be called as BCBV 3A. So, we have divided whole BCBV matrices into number of rows, and we have given names for each of the rows, and then we have divided your BIBC matrix into number of columns considering each column, and we have given names of these columns. So, consider if you are considering this column will be called as BIBC, since it is corresponding to it is getting multiplied to this particular entry every time of this matrix. So, since it is corresponding to node number 2 and B phase, it will be called as node 2 and B. So, it will be BIBC 2B. So, this is corresponding to your node number and this is corresponding to your phase number. So, this BIBC matrix will also be converted into number of columns, and if you see if you generalize structure of your BIBC and BCV based load flow analysis, it will be something like this. It will be having number of rows. If there are n number of unknown nodes into your system, all the 3 phase nodes consisting together, then this number of rows of BCBV will be, there will be n number of rows, and the size of this BCBV one row, it will be 1 by n. So, there will be one row and n columns, there will be n columns into this particular row. And if you see, observe this BIBC, it will be one column. So, it will be size will be n rows and it is column matrix. So, it will be 1. So, then this BIBC matrix will also be consisting of n columns if there are n 3 phase unknown nodes into your system. So, unknown nodes, if you are considering all the nodes except source node as unknown, then these 3 phase nodes will be considered here, and these are I nodes, generalized way, basically load currents, and these are voltage difference with respect to source node. So, we are taking the voltage difference of every node with respect to source 3 phase voltages. So, this is actually source 3 phase, these are basically source node 3 phase voltages, and these are actually unknown nodes voltages. This is structure of your direct approach based short circuit analysis matrices, and we are going to use them for short circuit analysis. And as I told you in last class, we have studied single line to ground. Let's start with now double line to ground fault here. So in this case, again consider any general bus. Say this is ith bus, this is I plus 1, and say I minus 1 bus, and since it is part of large system, I can just show it is other system is just dotted because it is part of large system. Then there is this is your B phase, again this is part of large system. Then this is your C phase, which is again part of large system. And since we are considering double line to ground LLG fault here, this I am considering fault on A and B phase, double line to ground fault. So this A and B phase is shorted, and it is shorted with respect to ground with ZF is equal to some value. There will be fault. This is fault impedance of this one. Now what will happen when the short circuit happens? There will be some current which is flowing from A phase. So this current will be post fault current. As I told you, comma F I am giving to represent the quantity which is post fault quantity, and A phase. So this is corresponding to ith bus, 8th phase, and it is post fault. Similar way, current which is coming from B phase will be, so this current will be given as I the bus current post fault and corresponding to B phase. Therefore, total fault current will be equal to addition of these two. So total fault current will be IIF A phase plus your B phase fault current. Therefore, if you write the nodal conditions, so I can write here the current of A phase will be basically post fault current of A phase, current in B phase will be basically post fault current of B phase, and current in C phase is basically C phase is not faulted, so it may be serving load current which will be negligible as compared to your fault current, so we can consider that as a 0. Similarly, all other load currents at all other nodes we can consider them as 0. Now if you see the voltages of these two buses, so voltage of B phase, say post fault voltage, so post fault voltage at B phase will be equal to it will be ZF multiplied by addition of both the currents, because both the currents are flowing. So this current multiplied by this impedance will be nothing but voltage at this point, and you can see that same voltage is coming at bus B also. So at both the places the voltage is same, so plus B. So this will be equal to your ZF plus ZF into fault current in B phase. And as we have seen that the same voltage is coming at A phase also. So for A phase also I can write this same condition, that at A phase your fault current is exactly same, because these both the terms voltage at both the terminals it is coming same. So it will be also equal to B phase fault current. Now let us see take our generalized equation here. So generalized equation which we have described earlier, where we have divided whole BCBV matrix into number of rows and whole BIVC matrix into number of columns, and this is nothing but your delta V matrix, and these are I nodes. And as we have seen, I node currents are almost 0 or negligible as compared to fault currents. So, therefore, all other currents we can consider them to be 0, like we consider for single to line guard fault. So, C phase current will be also equal to 0, and however, these two currents will be present. So, this current is A phase and this is fault current of B phase. So, only these two entries will be existing there, which will be replaced by fault currents in A phase. So, this will be fault current in A phase, this will be fault current in B phase, all other currents will be replaced by 0. Also on this side, if you see a delta V side, these two voltages we have calculated post fault. So, post fault these two voltages will be, this voltage we already calculated. So, this voltage post fault, this voltage will become ZF plus ZF B. Similarly, this voltage is also same. So, this also entry will also get changed by the same amount. So, here you just change these two entries with these two entries, all other quantities will remain same. So, if you modify this this particular matrix by changing these entries, means making these currents zeros except these two currents, and modifying these two entries to post fault voltages, I will basically get this matrix. So, as explained in earlier slide, I just modified these two entries here and these two entries here, and these entries are just post fault voltages I have written. So, here I just added your comma F terms, so that we can represent them as a post fault voltages. So, in case of double line to ground fault, your structure of BIBC and BCB matrix will be something like this, and from this we can easily see for any ith bus using these two equation I can easily write. So, it will be, so if you consider these two equations, this is one equation and this is equation 2, in this case these two entries will come into picture. So, I can just write it like this, only two rows, two equations I am taking, ZF into fault current in A phase. So, it is ZF multiplied by fault current in B phase on right hand side. Similarly, V1B minus A phase and fault current in B phase of ith bus, and this will be equal to, here these two rows will come into picture. So, BC, BV ith row and of ith phase, BC, BV of ith bus and bth phase. And if you see this matrix part here, from here to end, only there are two non-zero currents, this and this. Because of that, only column corresponding to these two currents. So, this column is corresponding to fault current in A phase and this column is corresponding to fault current in B phase. All other columns, if you observe, they are getting multiplied with respect to 0. So, the equivalent matrix of structure or equivalent matrix of this system up to this, it is actually BI, BC, A phase. Just I have to take this column and I have to take this column here. So, it is, and it will be getting multiplied by these two entries. All other columns actually getting multiplied by 0. So, we are not considered while writing this particular equation here. Now, if you write this equation in simplified form, so if you just simplify it, I will get this equation here. So, V1A, V1B minus ZF, 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 ZF into fault current in A phase, fault current in B phase is equal to BCBV matrix rows corresponding to A phase and B phase of ith bus, and then column of BIBC corresponding to ith bus and A phase, and BIBC column corresponding to I and B, ith bus and bth phase, and this again we have seen that it is getting multiplied with your fault currents. So, basically we are getting this equation here, and in this particular equation we are interested in getting fault currents from A and B phase. So, we can just simplify this equation so that we can write them in terms of fault currents. So, I can just write it like this. So, V1 I can just take this term on right hand side, and these currents are actually common, we can take it out. So, if I simplify it, I can just write it like this. So, this matrix is BCBV of B phase, and then columns of BIBCs corresponding to A phase and B phase of ith bus, plus you are getting this ZF matrix on right hand side, and this is getting multiplied with your fault currents. And if you observe, I am calling this particular part as Z short circuit matrix in case of LLG fault, and so this particular equation will become equal to V1A, V1B will be equal to, so this part I am calling short circuit matrix of LLG fault, and here it will be fault current in A phase and fault current in B phase, and then we can actually calculate fault currents, because this part is known because these are source voltages at bus number 1 which are basically known, and the fault currents in A and B phase will be equal to the inverse of this matrix, which will basically 2 by 2 matrix LLG, and we need to take inverse of it, and this voltage is basically known, we can calculate fault currents. So, this is how using this equation we can calculate fault currents in double line to ground fault. The post fault voltages in this case can be calculated similar way like we have calculated in case of LG fault. So, that same equation which we have taken it here, I am taking it again here, and if you see this, if you want to calculate this particular post fault voltage, then we need to write the equation for this. So, if you write the equation for this, it will be V1A minus V2 post fault A will be equal to this particular matrix part, that is BC BV 2 of A phase, bus number 2 and A phase. So, we have to consider this row corresponding to this, and we have seen that the equivalent of this part of matrix equation is having only these 2 columns are getting multiplied with non-zero current, otherwise all are getting multiplied with zero currents. So, we can write them like this. And the fault currents we already calculated, and those fault currents are fault currents in A phase and fault currents in B phase. We have seen how to calculate in last slide, and therefore we can write post fault voltages of A phase of bus 2 will be equal to V1A minus this matrix part here, that is BCBV 2A of B phase. This row will be 1 row multiplied by, so this is actually row, so that there will be n columns in that, so 1 multiplied by n. Size of this you observe, it will be actually 1 column n rows, so n multiplied by 1, so total size will be n multiplied by 2 here. So size of this part will be actually, there are 2 columns and n rows, so that is why n rows and 2 columns, and size of this current part is actually 2 rows and 1 column. So overall if you see, so from this we will get 1 multiplied by 2, and from this you are getting 2 multiplied by 1, so finally you will get 1 by 1 size matrix, which is actually basically you will get voltage here. Similar way, generalized way, if you want to write the voltage equation using whatever we have done in case of LG fault, I will just write them here. So it will be Vj post fault will be equal to V1 minus BC BV corresponding to any jth bus where we want to calculate post fault voltages, and this will get multiplied with respect to BI BC as I have shown you, only these two columns are getting multiplied with respect to fault currents and multiplied by your fault currents. Sorry, this is fault current. So this is the generalized equations to get the post fault voltages of any jth bus. In this case, J might be changing from 2, 3 up to n 3 phase buses. So instead of that, actually I will just write small n. So small n 3 phase buses where I do not want to take I or j not equal to I. So ith bus we already fault has occurred. So except ith bus we can calculate voltages of any jth 3 phase bus here. So basically this will be this matrix, if you expand, it will be Vja, Vjb, Vjc post fault. So all the post fault voltages of jth bus, all the 3 phases will be equal to this particular matrix will be V1a, V1b, V1c for all the 3 phases minus this particular matrix will be having all the 3 rows. So BC BV JA, BC BV JB, BC BV JC. So collectively I can write it like this. However, this part will remain same. So here this BI, BC we are already considering the faulted phases here A and B, and this is getting multiplied with fault currents which are already we have calculated before calculating post fault voltages. So fault currents are known before calculating post fault voltages. So by using this particular equation you can get post fault voltages at any bus. Now let us see triple line to ground fault, and in case of triple line to ground fault, the ground fault occurring three phase to line, three phase to ground. So let us say in this case also let us consider any ith bus. So this is I plus 1th bus, this is say I minus 1 bus. So this is say corresponding to A phase, then corresponding to your B phase, and this is corresponding to C phase. And in this case triple line to ground fault is occurring, means all the three phases they are getting short circuited with impedance of ZF. So fault impedance is ZF. So this phase also getting short circuited here, this phase is also getting short circuited. So all the three phases will carry short circuit current. So terminal condition I can easily write. So in this case I can write the current of A phase will be basically fault current of A phase, current of B phase will be basically fault current of B phase, and current of C phase, because all the three phases are shorted, current of C phase. And now if you see the so this is actually your current with fault current in A phase, this is your fault current in B phase, and this is your fault current in C phase. So here there will be total current. So the current flowing to the fault will be addition of all the three currents. Now post fault if you observe the voltages of these three buses A, B and C, they will be same, because these terminal voltages will be same, which will be just, so I can just directly write V post fault voltages of A phase, post fault voltages of B phase and post fault voltage of C phase will be equal, and that will be equal to your ZF multiplied by all the three currents, addition of all the three currents, current in B phase, fault current in C phase. So that will be equal to ZF into fault current in A phase plus ZF into fault current in B phase plus ZF into fault current in C phase. Okay. So we have got the terminal conditions of or boundary conditions for this particular fault. Now we will try to fit these quantities into our general matrix of direct approach. So general matrix of direct approach we already seen, it is rows of BCBVs and columns of BIBCs, and what we did earlier is we just replaced your current values on right hand side and fault voltages values of faulted buses on left hand side. So basically we have changed this and we have changed this here. So let us see what change will happen. In this case all the three phases are faulted. So as compared to fault currents in ith bus, all other bus currents will be negligible because they are just serving the load currents. So all these currents except these currents will be, except these currents they will be 0, and we have seen that this current IA is actually fault current of A. So I can just replace this by this one, and in B phase there will be fault current in B phase also, and then C phase there will be fault current. So these three entries will be get replaced by fault currents of these three entries, otherwise all entries will be 0. Similarly post fault voltages on left hand side, so these three entries, so VIA, VIB and VIC will be replaced by post fault voltages at that particular bus, and all they are same, and these will be getting replaced by this particular term here. So, if you see this term, if you put this term in all the 3 locations and all the replace these currents with fault currents, you will get this equation here. So, here I just replaced post fault voltages of all the 3 phases, and here I just replaced by faulted currents. So, during the fault condition, your structure of your direct approach based matrices will be something like this. Now, in this case also, just first take these 3 rows corresponding to faulted bus. So, if you take these 3 rows corresponding to faulted bus and write them separately, the equations will be something like this. So, it will be ZF into minus ZF into B phase fault current minus ZF into C phase fault current. Similarly, I can write for B phase, it will be ZF multiplied by A phase fault current, ZF multiplied by B phase fault current, C phase fault current, and then C also we are getting similar terms. So, it will be minus here, ZF multiplied by A phase fault current, ZF multiplied by B phase fault current, ZF multiplied by C phase fault current, which will be equal to, you are having this 3 rows which will come into picture. So, this is BC BV row corresponding to A phase, BC BV row corresponding to B phase, BC BV corresponding to C phase of ith bus. And again, if you observe this matrix part here from here to here, these columns are getting multiplied with respect to 0 except these 3 columns here now. Now, these 3 columns are getting multiplied with respect to this non-zero fault currents, otherwise all other currents are 0. So, therefore, simplified form I can write it like this. BIBC column corresponding to B phase, BIBC column corresponding to C phase of ith bus, and this is getting multiplied with the fault currents in A phase, fault currents in B phase, fault current in C phase. Now, we are interested in getting these values of fault current. So, we can simplify it to get that. So, if you can simplify this equation here, you will get V1A, V1B, V1C will be equal to, or we can say minus here, you are getting ZF matrix 3 by 3 and this is getting multiplied with fault currents of A phase, fault currents of B phase and fault currents of C phase. This basically I am writing from this part. If you see, this ZF is getting multiplied with respect to various currents here, and this part I am just writing in matrix form, which will basically come like this here, which will be equal to your BC BV matrix, and as I have seen here there are 3 rows of BCB matrices. So, corresponding to A, BCBV row corresponding to B, BCBV row corresponding to C of ith bus, and BIBC corresponding to A, column BIBC column corresponding to B, BIBC column corresponding to C of ith bus, and this is getting multiplied by your currents C. Now we can take this term on right hand side and take fault currents common out. So we can get this matrix here. BCBV row corresponding to A, BCBV row corresponding to B, C, and then BIBC column corresponding to A, B, and C, and plus your Z matrix we are taking on right hand side. So ZF, 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 and this is getting multiplied with respect to fault current in A phase, fault current in B phase, fault current in C phase. And this particular matrix from here to here, I am calling it as Z short circuit matrix for triple LG fault. So this will be equal to, then on this side it will be V1A, V1B, V1C, and here it will be all the three phase fault current, that is fault current in A phase, fault current in B phase, and fault current in C phase. So I can easily write all the three fault currents in A phase and B phase and in C phase. All the three fault currents in all the three phases will be equal to the inverse of this short circuit matrix of all the three phases. You have to take inverse of it, and then V1A, V1B, and V1C. And as I told you, the voltages of first node they are known to us, and then this matrix will be also known because it just depend on your BIBC and BCIB matrices and fault impedance. So this is also known, and if you get this matrix and voltages of first node, you will get the fault current into the system automatically. So this is how we calculate the fault currents in triple line to ground fault case. The calculation of post fault voltages will be exactly similar like we have considered in case of single line to ground fault as well as double line to ground fault. In this case also you can use the same equation which you have used. So here we have this equation, I am directly writing it. So Vj, we have seen that it will be equal to V1 minus we have this BCB matrices corresponding to J, and then in this case you are having this three columns of the simplification of this part of the matrix. You are seeing it is BIBC. You are having three columns, because only these three columns are getting multiplied with non-zero currents, and these currents are currents in A phase, current in A phase, current in B phase, and then fault current in C phase of ith bus. So this particular equation, so in this case J is changing from node number 2 up to small n 3 phase nodes, where J is not equal to I, because you are not calculating the post fault voltages for faulted bus, remaining bus you are calculating. So this is how we can calculate post fault voltages. So as I explained in last part, this will be your three phase matrix which will be consisting of three bus voltages which are post fault voltages of A phase, B phase, and C phase. So the expanded form of this particular matrix will be something like this: expanded form of this particular matrix will be V1A, V1B, V1C minus expanded form of this particular part of matrix will be BC, BV, J corresponding to A phase, BC, BV, J corresponding to B phase, BC, BV of jth bus corresponding to C phase. So, basically we are taking all the 3 rows corresponding to jth bus where we want to calculate post fault voltages, and this part will remain same. BIBC column corresponding to B phase, BIBC column corresponding to C phase, and this will get multiplied with fault currents which are already calculated. So, when you are calculating post fault voltages, post fault currents are already calculated. So, using this equation you can get post fault voltages of various buses or various non faulted buses. So, in this particular lecture we have seen 2 faults, those are double line to ground fault and triple line to ground fault. So, we have derived the matrices or equations for fault currents. In case of double line to ground fault, there will be 2 fault currents in 2 phases. In case of triple line to ground fault, there will be all the 3 phase currents which are faulted currents. So, we have derived the equations for them, and then we also derived the equations for post fault voltages. Basically, equations for the post fault voltages will be same for almost same for all the types of faults. So, here we will stop today, and next class we will see few more faults. Thank you.